Let's review radical properties. Using properties of radicals. A radical expression is an expression that contains a radical. What we're talking about is this symbol right here. Okay. So if we got the square root of a, we don't know if it's a square root or not, but we use what's called the index like this. Actually, it might be even better if I use x as my variable, and this is b, and that is a. Okay, which is the same thing as x to the a and the root of b. Those mean the same thing. An expression involving a radical with index n, or in my case b, is in simplest form when these three conditions are met. No radicands, that's the thing underneath. Okay, this guy right here is the radicand. No radicands have perfect nth powers as factors other than 1. So if you can reduce some factor powers out of here, if there's a square in there somewhere, you got to take it out, or a third root or a fourth root, whatever the root may be. No radicands contain fractions. You can't have a fraction inside the radical symbol. You can separate it, and then you can rationalize the denominator. And no radicals appear in the denominator. That's the part we were just talking about. Square roots are the easiest to fix. Cube roots and fourth roots and fifth roots and so on are okay to fix. They're not that bad. You just have to do a little thinking first. Okay, so the product property of square roots. If you have two numbers multiplying underneath the same radical, then you can separate them into the same kind of radical. Okay, which then means you can separate those pieces. That's how we're separating, especially square roots, whenever we do our factor tree. Okay, so if you had a cube root of 9 times 5, it would become the cube root of 9 times the cube root of 5, which doesn't really help us because neither of those have a cube root. But it could come in handy in the future. So here's an example here. So the square root of 108, we can break into 36 times 3. That's just like us doing this. And then 36 can be broken into 6 and 6. And we've got a pair of 6s, and we got our 3 left over. Okay, that's how we do the factor tree method. What we're looking for is this 6 times 6. That means 6 squared, and this is an index of a 2. So we're looking for what is being squared. 6 is. So the 6 comes out. What isn't being squared? The 3. The 3 stays in. 9 square roots of x to the third. Well, this becomes 3 times 3. There's my pair up, square up. It gets to pop out. What's being squared? The 3. Now, x is an interesting one when we do variables, because you could break it into x squared and x, and there's your squared thing. So what gets to come out? X does. And what doesn't? Well, x. The way I like to do the variables is I like to just take whatever index I am and divide the exponent of the variable by that number. However many times it goes in wholly is how many times it comes out. 2 goes into 3 one whole time. And whatever's left over, the remainder, is the exponent on the inside. So how many times it goes in wholly, exponent on the outside. How many remainder, exponent on the inside. Another property, quotient property of square roots. If you are dividing a square root or a cube root or a fourth root or a fifth root, you can separate it into separate radicals, top and bottom. Then you have to rationalize it because you can't have a radical in the denominator. We have to take that irrational thing out and rationalize that denominator. So if you want to use the quotient property, all you do is take the expression you have, separate it. Square root of 64 is 8. Great, that went good. Square root of 15 isn't, because 15 is 3 and 5. No pair up, square ups. When we do b, separate them into their pieces. Square root of 81 is 9. Square root of x squared is x. So it's great. Okay. You can extend the product and quotient properties of square roots to other radicals, such as cube roots. Okay. When you have odd roots, you can actually have negative radicands. With even roots, you got to do, well, square root, you can do the I, which is square root of negative 1. With other even roots, you just can't. But with odd roots, you actually can. Odd roots start however they finish. If they start as a negative, they finish as a negative. If they start as a positive, they finish as a positive. And so let's look at, just skip all the way down to B, and let's look at that one. I would take that 3, okay, you're going to do your 125, which is 5 and 25, which is 5 and 5. And we're looking for 3's. There's 1, 2, 3, 5. So what gets to come out? 5 does. They cubed up. The other one is the x. I would divide it by 3. 3 goes into 7 twice. So notice that x squared is what comes out down here. And what I have left over is 1x on the inside. Okay? Because basically what's happening is you have x times x times x times x times x times x times x. Cube, cube, and x comes out for each, which is x squared, stays inside. Just like that. Rationalizing the denominator is one of the hardest ones. Okay, square roots aren't that bad because a square root squared is the number underneath. So if we have a square root on the bottom and we need to get rid of it, multiply by its exact self. Square it, because square and square root cancel out. So 3n times 3n is squared. Square to square cancels out. Just do it top and bottom. Cube roots and fourth roots are a little different. If we've got 2 over the cube root of 3, to get a cube root out, we need 3 of something. Right now, I only have 1 of something. So I would have to multiply by the cube root of 3 squared. The cube root of 3 squared. That would give me 2 cube roots of 3 squared over, then I'd have the cube root of 3, because it's the same radical index. They're both cube roots. The bases of the radicands are the same. We add the exponents when they multiply. So to the third. Cube root of third cancels out, so it'd be 2 cube roots of 3 squared over 3. The cube roots and the fourth roots gets a little tricky because some things need more things than others. So like if we had 3 over the cube root of 2x squared, I need 2 more 2's, but I only need 1 more x. So I'm going to multiply by the cube root of 2 squared x. And the reason for that is I have 1 2 and I need 3, so I need 2 more 2's. So that gives me the cube root of 2 cubed. I have 2 x's, I need 1 more x. So that's x to the third. All that cancels out. Leaves me with 2x on the bottom. And then the top just multiplies, and 3 doesn't get to go in, so it's just 3 cube roots 2 squared x, or you could say 4x, like that. The binomials. If you have a binomial with a radicand at the bottom, just like we saw with I, or like you will see with I, if you have an irrational in the bottom and it's a binomial piece, to get rid of it, you multiply by what is called the conjugate. And the conjugate just is change the sign. Everything else stays the same. So if we have 7 divided by 2 minus the square root of 3, the conjugate of minus is plus. So we multiply by it top and bottom. When we do the FOIL on the bottom, the O and the I terms, the linear terms, end up canceling each other out to 0. And so we're left with the first term squared minus the last term squared. The square root of 3 squared, square and square root cancel out, leaves you with 3. And if you have 4 minus 3, you get 1. 2 times 7 is, or 7 times 2 here is 14. 7 times that is 7 squared is 3. And so that's where you end up. Radicals with the same index and radicand are called like radicals. You can add and subtract like radicals the same way you combine like terms. It basically becomes an x, or a unit of measure, because the number in front, the coefficient, is how many you have. So like in this first example, 10 square roots of 5 plus 20. Well, those don't add right away because they both have a square root, but they're not both 5. But 20 becomes 4 times 5, which is 2 times 2. And I get to pull a pair out, and now it's square roots of 5 and square roots of 5. So it's I have 10 of them, and I have 2 of them, so I have 12 of them. Okay, they do it in a weird distribution way. I just think, okay, my radicals are the same, so that's a unit. It's like I got 6 bananas and 2 bananas. I got 8 bananas. And it works just like a like term. Multiplying works As long as the index is the same. You can't do a square root times the third root, but as long as it's square root, third root, numbers underneath can combine and multiply together. Okay, so like square root of 14 times square root of 7. Square root of 14 makes it nice because that's a 2 times a 7. And 7 is itself, so it's going to bring another one. So 7 is going to come out, 2 is going to stay in. If we have square root of 5, so we're going to square root of 15 in, minus, now 75's got 25 and 3, which is 5 and 5. That pairs out, okay, just like that. And that makes them the same radicands, and then we can subtract their coefficients. 1 square root of 15 in minus 5 square root of 15 in, negative 4 square roots of 15 in. Okay. And then dividing. You don't. Simplify it so you know exactly what you need to multiply by. Like you can multiply by the square root of 30, but that's just a lot of extra factors you don't need to deal with. Simplify it first if you can. Okay. And so see that these radicals could be combined together into one radical. And then if we think of it as the square root of 10 over 30, we drop that down. We got the square root of 1 over 3, and then we can break it back into square root of 1 over square root of 3. Square root of 1 is 1. So we can simplify the 3 and the 12 as well, because they're whole numbers. 3 goes into 3 once, 3 goes into 12 4 times. That's how they get the 1 on the top and the 4 on the bottom. Square root of 1 is 1. 1 times 1 is 1. Now what we can't have is that square root down there. We don't have to worry about the 4. We have to worry about the square root of 3. So multiply it square root of 3 top and bottom. Square root times itself is the number underneath. So 4 times 3 is 12. Square root of 3 times 1, square root of 3. So let's do a couple practice problems from each page. All right, we're doing the cube root. So let's see, 56 is 2 times 23. And 23 is a prime number. And k, we divide that, 3 doesn't go into 2. So that's going to be the cube root of 56k squared. That's exactly as far as it goes. Now, there's this if necessary, use absolute value signs. That comes in whenever you square root a variable. Remember, when we square root, or any even root of any even variable, if we square root something, like 9, it could be 3 times 3. But it'd also be negative 3 times negative 3, and we don't know which one it is. So when we solve, we actually get plus or minus as an answer. But if we're just simplifying, we want to know we take the primary, the positive one. So if you even root an even exponent and get an odd exponent, use absolute value. Just around that exponent that does that weird thing. So I'll show you how that goes. 3's got a good example of it, so we'll do that. All right, square root of 176. Well, it divides by 2. 76 divided by 2 is 88. And that's 8 times 11. That's 2 times 4. That's 2 times 2. There's a pair. There's a pair. And 11 stays in. So 2 comes out, 2 comes out, and 11 stays in. So that's 4 square roots of 11. So I guess it was 16 times 11 originally, because if you go back in a radical, you're going to square in, or whatever the index is. But let's look at number 3. 4th root, 81's 9 and 9. I don't pair up, square up, because I'm looking for pairs of 4. I go 3 and 3, 3 and 3. Everybody's broken. There's my 3. So 3 is going to come out. Now when I divide the w by 4, I'm just going to get, 4 goes into 4 once. I just get w to the first. Now this is an even that results in an odd. So I have to put the absolute values around the W part. Not the 3, just the W. 3 is a positive 3. If it was negative, I'd have a minus on it. But W, we don't know. So we want to make sure it stays positive and get the primary answer. So we put that absolute value bar around it. Okay, to add and subtract, they have to be the exact same radical. There's a 1 there, there's a 1 there, ends up as 0, because negative 1 and 1 makes 0. Now here, like sign going to combine. They have both square roots of 7, so negative 5 of them, negative 4 of them, negative 9 of them. Now this one, I should simplify first. It's a pair of 2's, and a 2 stays in. So that's actually 2 square roots of 2. So 2 of them, 1 of them, and 1 of them equals 4 square roots of 2's. So simplify it first, then put together what you can. When you multiply, ooh, that's a nice little foily situation we got going on here. What's inside goes. I'm just going to multiply it all first. This times that is negative. Negative makes positive 5 square roots of 49b to the 4th. And then outside, negative 6 times 35b squared. And here, positive 35 square roots of 35b squared. And outside, negative 42 square roots of 25. And we're going to mess all this bad business down. Square root of 49 is 7. 7 times 5 is 35. The square, let's see, we divide that by 2, goes in, that's a b squared. Square root of 35 isn't, but b squared is, so that's minus 6b. Now, even root, even thing, that should be absolute values. And we should get square roots of 35 in there. 35 doesn't have one, but the b is going to come out, so plus 35b square roots of 35 minus square root of 25 is 5, whatever 42 times 5 is, 210. 210. All right, we've got like things here with square roots of 35s, and we've got 6b's and 35b's. So 35b squared minus, no, plus 29, absolute value of b, square roots of 35 minus 210. And none of the rest of those get to mix because they're not all like terms. That's a big nasty one, but good times, good funs. If you got a little baby calc, if you only got one variable, it won't do the variable parts. I lied. So you got to do it all by hand. All right, let's do these bits. I might square root 44 first. I know that's 4 times 11, and that's 2 times 2. 2 comes out, so that's 4 square roots of 11c. 18 is 9 times 2, and that's 3 times 3. So that's times negative 15 square roots of 2c, because that stays in. And when we multiply them together, we're going to get negative 60 square roots of 22c squared. Divide that by 2, so that's going to be negative 60c, absolute value, square roots of 22. Absolute value comes because we did an even root of an even exponent and got an odd answer. So you do them just like that. Dividing. You can't have a radical on the bottom. It can't simplify, so I'm just going to multiply by the square root of 7, top and bottom. So that's square root of 14. Those multiply together over 7. Okay. I'll do one that has a conjugate to it. The conjugate of 3 minus 7 square roots of 7 is 3 plus 7 square roots of 7. Okay, let's do my FOIL. I'll do it up here in a box. So that was 3 minus square root of 7 square root of 7. 3 plus 7 square root of 7. That's a 9. That's negative 21 square roots of 7. It's positive 21 square roots of 7, so those cancel out, and we're left with negative 49 times 7. What's 49 times 7? 343. So that's a 343. So 3 minus 343 is going to be negative 340. So we get negative 340 on the bottom. And on the top, 4 times 3 is 12. And 4 times 7 is 28. Square root of 7. Let's see. 4 goes into most of those. Let's see if it goes into 340. Clear. 340 divided by 4 is 85. So this is going to reduce to 3 plus 7 square roots of 7 over negative 85 because they all have a factor of 4. Number 2, it just needs a square root of 11c. That would make that go to a 2 and that go to a 2. So 7 square roots of 11c minus 6 square roots of 55c squared over 2 times 11c. Getting fun. So 7 square roots of 11c minus square root of 55 doesn't, but c comes out. 6c square root of 55 over 22c. Those go. No, they don't, because it's got to be in everybody. So it's going to stay just like that. Good times. Make sure that radical stays over there, and that's an 11, not in anything else. That's product.